Good morning. I'm very honored to be here and a little bit daunted by the audience. I want to thank Peter and Alex for inviting me. In fact, as Peter started his introduction, I realized it would be perfectly good and perhaps much more economic to have him give the whole talk. But anyway, I'll do my best this morning. I really come to Emergence as a bit of a hobby. I'm constantly telling my students that science is not purely deductive, but it's actually much more like poetry, and that like any artist, you will encounter long periods when things don't go well, and that frankly you're depressed, then you have a good idea and it fails. And so I take solace in looking at history and going back and realizing that it was tough back then and it's probably tough now. And similarly, just back then they thought that they were not in a revolution, and we also don't really think we're in a revolution, but in fact quite often the optimistic viewpoint holds out. And so I came together with some philosophers about 3 years ago and gave them a talk. We discussed for a long weekend in Durham about what emergence is, and boy, those philosophers, they really have a very different point of view to us, including the way they do seminars. And out of it came, we're really the rowdy group compared to the philosophers, came this little article here, which is in the Routledge Handbook of Emergence, and mine was one contribution to this. And so this is really a version of that talk adapted to the physics audience, okay? It's not really my normal mode. I'm a fully functional and operational research scientist, but I thought I would tell you a bit about some of the history and why there's cause for optimism, okay? And so this little picture here is a picture of the cosmos, but it has two pictures from the lab. And one of the things that we all know and should realize is that the lab is connected to the cosmos. And just as Isaac Newton got his inspiration from a falling apple, Higgs and Anderson took their inspiration from the levitating superconductor. And so what I'm going to try and emphasize is that deep understanding of physics often requires that we decode its emergent consequences. Okay? And I'm going to give you some examples of that. Here's my over-ambitious outline. And I'm going to talk about reductionism and emergence, and following what Peter remarked, I'm going to talk a bit about Weinberg's view, Anderson's view, but then going back to the 17th century, we'll talk about Francis Bacon's view. He was an early proponent of the experimental approach to science, one that has really kept us going for 4 or 5 centuries. It's the driving force of the Renaissance science movement, which we are part of, and Holland played a major role in. I'll talk about emergence in classical physics. Where's the emergence in classical physics? We'll come back to that. I'll then go on to what Peter already referred to, Anderson's viewpoint that more is different, and we'll look at this amazing gulf that separates the angstrom from the micron. We're accustomed, we're taught that the great frontiers are the very large and the very small, and that to understand gravity we have to go down to the Planck length. But actually there's a remarkable frontier that lies between the angstrom and the micron, just 4 orders of magnitude, and that's one that is an equally important part of the frontier. We'll come to that. And lastly, I will tell you a bit about emergence in the 20th century condensed matter physics. I'll take a few examples and show you how emergence is working today. Okay? All right, so emergence and reductionism. Well, what is reductionism? Reductionism is that marvelous idea that as we take matter apart to its smallest constituents and understand the laws and forces that govern them, we can understand everything. And this viewpoint has been immensely successful. It's an idea that goes back to the Greeks, and it's in our DNA as physicists. We cannot live without the notion of reductionism. If we abandon it, we are surely lost as physicists. Okay? On the other hand, emergence, by contrast, is this intriguing idea that as matter comes together, it develops novel and unexpected properties and patterns of collective behavior. And when we walk outside this afternoon and the snow begins to fall, we're reminded of that. A snowflake is an emergent property, a flock of geese flying south in the wintertime. If we're lucky enough to have done it, you can hold a modern high-TC superconductor in the palm of your hand and watch it levitate a magnet. It's a remarkable thing to do, because when you turn that system upside down, the magnet stays beneath and just hovers beneath the superconductor. And last but not least, all around us in this room is living proof of emergence, life itself. Okay? And so all of these are examples of natural science that are not simple extrapolations of the microscopic laws, and that often require new concepts to be understood. So, back to those guys who constantly argue, Weinberg and Anderson. And sometimes these arguments got very, very heated. And it's quite common amongst particle physicists to learn that that guy Anderson is the guy who stopped the superconducting super collider. In fact, he didn't do anything of the sort, but he could have done things more diplomatically. So here are their two books, Dreams of a Final Theory, and Anderson's More and Different. And reductionism and emergence are sometimes presented as opposites. And it's not hard to understand why the people who support these ideas are very forceful in their viewpoints. Weinberg, in Dreams of a Final Theory, which is a beautiful book, describes wonderfully the dream of how all of nature can be reduced to a final theory. And he does discuss reductionism in this book, but he says it's not really the true frontier. The real thing is the dreams of the final theory. By contrast, Anderson, as Peter just mentioned, points out that science, going all the way up from the Planck energy up to atoms, on up to sociology, the brain, and above all these things, lawyers, is governed by emergence. And each level in the hierarchy of understanding involves emergent processes, and there's no real reason to believe that fundamental physics is the smaller scale. It's not tied to the level of the hierarchy. Okay, and of course one can extrapolate that to say that fundamental physics is gumph, which is stupid. Okay, so these two viewpoints, they really don't repudiate one another. And why should we think about this? Can't we get on with our experiment? Well, I think it's useful for us to think about what emergence and reductionism are, because we might be able to pragmatically use that understanding to our advantage to accelerate our science. Okay, and so I will take that pragmatic point of view that reductionism and emergence are complementary, and that they're linked by experiment and they drive each other. And you probably can't ever separate the two. And if you do, your science will come amok. And we'll talk about this, but it's not my idea. This is an idea of an ancient Renaissance scientist, the philosopher-scientist Francis Bacon, who not only talked about experiment, he actually did it. And here's what he wrote. I'm not going to read it out to you in detail. He said that there are two ways of uncovering and investigating and discovering truth. And the one was the Greek approach, starting from your axioms and deriving everything from them. This is really reductionism as we know it, okay? And as he said, this way is now in fashion. It really was the viewpoint before the Renaissance, okay? And the other, which is what he was pushing, is the idea that you basically do experiment and you don't make presumptions. But nevertheless, you do aspire to a reductionist viewpoint. It's just that you don't start from the full theory at the beginning. You gradually work your way upwards, okay? And he mentions that this is the true but as yet untried way, okay? And of course, it's been tremendously successful. It's this approach that led Orville and Wilbur Wright to actually make a fully functioning airplane. They didn't start with a full-fledged jumbo jet. They started with little gliders and worked their way upwards, okay? And it's a viewpoint that might be taken to heart by those who are trying to make quantum computers. And so let's move on a little bit and this was in 1620, and talk about an example which is very useful, emergence in the classical world. And we're taught that classical mechanics is the ultimate reductionist construct. It's almost perfect. And you can derive everything starting from Newton's laws or Lagrangian mechanics. Okay? So where is emergence in that? Well, you might think that it's in the complexity of the thing when you put many things together, but actually it's right in at the core. And it caused a big problem for almost 200 years. And I'm going to tell you that story. Okay? Okay? These are the great scientists of the emergent era: Isaac Newton, Gottfried Leibniz, Louis Lagrange, and William Rowan Hamilton, with this lovely picture from a 48 cent, and that's 48 cents of a euro. Energy, the reductionist consequence of classical mechanics, was unknown for almost 2 centuries after Principia. How can that be? It's the fundamental thing of classical mechanics. We should pause and think about this, okay? Okay. It was an unknown concept to the greatest minds of the era. Newton and Leibniz argued over it, something related to it called vie vivre, and even Lagrange and Hamilton didn't know about it. Hamilton, who called it H. Okay? Okay? So why? Why were they missing all this stuff? Okay, so let's go and look at that. Let's take ourselves on a little historical journey back to 1758. This was 72 years after Principia, and the classical revolution was in full sway. It was something that fascinated the people of Paris as they looked in the night sky and looked at this fearful thing, Halley's Comet. It calmed them to understand that they could understand such things with classical mechanics. And so the publishers in Paris decided to bring out the first French translation of Newton's Principia. This was the first European edition. In fact, it was the first edition you could understand if you did not read Latin. And here it is, and you'll see that the author is Madame la Marquise de Châtelet. Okay? And Châtelet was an amazing person. Let me tell you a bit about her. The Marquise Émilie de Châtelet was a natural philosopher, a translator and interpreter of Principia. In fact, her publication, which came out 10 years after she died, would be regarded today as a Rev Mod physics. Okay? And she discussed, and by the way, she was a brilliant mathematician. Today she would be a string theorist. She was the string theorist of her era. Okay? She knew about calculus, and she was the first person to formulate Newton's laws, not using the dots that Newton used, but using the Leibnizian calculus. And one of the things she discussed was this big argument between Newton and Leibniz, who favored vie vivre, something which he couldn't really derive, but was mv squared, and Newton's quadratus motus, which of course is modern momentum. And there was a controversy about these two things. Neither denied the importance of momentum, but this thing, vie vivre, was something they couldn't quite get their hands on. The resolution of the controversy required understanding of an emergent phenomenon, heat. Okay? And here's Mr. Count Rumford, who was a patriot, an American patriot, who left North America and made his way to Munich. And in Munich, he did his famous cannon boring experiment, which debunked the caloric theory of heat. Okay? And here's his design for the cannon boring experiment, and here's his little quote about that heat is motion. Okay, and this was already at the very beginning of the 19th century. Okay, so here's the background history. In 1788, Lagrange introduced T equals half mv squared. He knew that T plus V was constant. You can read it in his treatise. But he didn't take it further. And by the way, he didn't call anything by their names. He just labeled everything as T and V and L. And that's what he did. He didn't give concepts, because that was not the way of the day. Hamilton, building on Lagrange, also knew that T plus V is constant, but he called it H. Okay. Thomas Young was the first person to introduce the word energy, and he didn't really have a good mathematical understanding. He didn't know about Lagrangian physics, but he had this feeling that here was a new concept, and he should give it a Greek name. And Coriolis, in somewhere around the same time, 1824, introduced the term work. And the idea of energy conservation, however, came really from experiment. And it was Joule, and then later the great theorists, Kelvin, Rankine, and others, who introduced the concept of energy conservation. Okay, and so the point is that the greatest minds of their generation couldn't understand energy because, of course, energy, unlike momentum, dissipates into heat. It's not a vector, it's a scalar. So when things collide, it becomes randomized, and it seems to vanish, okay? And you might say, well, look, maybe these guys weren't reductionist enough. If Lagrange had taken his equations literally, maybe he could have derived the conservation of heat, okay, conservation of energy, right? But the fact is that these guys didn't do that, and it was really experiment that enabled them to unearth one of the most remarkable emergent consequences of classical mechanics, which is heat. And in fact, it's interesting that entropy was introduced before heat in the history of physics, before energy. Okay, let's now move on and talk about the traditional frontiers of physics. And I, like many other theoretical physicists, was thrilled as a kid to hear about the great frontiers of physics. And one of the things that we cannot deny is the tremendous power of reductionism. Atoms, relativity, quantum mechanics, the prediction of antimatter, the discovery of gauge symmetries. These are really a monumental tribute to the power of reductionism. We can't give up on it. It's really important, okay? And these are marvelous books that capture the beauty and romance of this discovery. But there's a downside to these beautiful books, and because they give an impression that the frontier of science is purely reductionist. It's the very small and the very big. What are those frontiers? Well, they're amazing. The hunt for dark energy, the discovery of gravity waves, the discovery of the predicted Higgs particle, and perhaps, if we understand string theory, the string multiverse. These are the great frontiers of physics that you can read about in the Elegant Universe. Okay? But it's not everything, okay? And we've heard about Anderson, and it's obvious that when you look around you that there's much going on that is not directly deductible from the microscopic laws of physics. And in fact, all of these aspects of physics involve physics, well, except maybe dark energy, involve physics on scales way below the angstrom, the size of an atom. Okay? Let's look at that a little bit. As we go up, we see remarkable emergent phenomena, and most of these things develop as we go from atoms up to larger scales. Okay? Our world sort of ends around the micron, unless we have special machines to look smaller, okay? But reductionist physics certainly works beautifully on the scale of the atom, around the nanometer or an angstrom. Here, in this domain, we really have no doubt about the laws of quantum mechanics. They work remarkably well, okay? And we can take them up, and with a lot of work, we can understand amazing things like superconductors. And the astonishing thing is that if you take tin or lead or gold, they're no different on the atomic scale. But as you put them together, gold acquires all of its marvelous properties, its luster, its metallic properties. But lead and tin on this scale, the electrons come together to form Cooper pairs. And the size of a Cooper pair in tin is around 230 nanometers, a quarter of a micron, almost observable. Okay. But if we go beyond that, Okay, and by the way, we talked about the multiverse, but we have the periodic table emerging from atoms, and this is, of course, driven by quantum mechanics, and it's worth thinking a bit about quantum mechanics for a moment. First of all, the wave function of something that you can hold in your hand involves more particles than there are stars in the known universe. Okay? And so a wave function is a function of each of those stars. Okay? Moreover, it's a wave, and when you add waves together, they interfere, and so the sum is different to the sum of its components. And that's why when you mix stuff together, you get what Newton thought was alchemy, but is in fact chemistry. Okay? And chemistry is amazing. And the periodic table is really, it's really the fabric, the canvas on which emergent physics develops at the quantum level. Each new material is a new multiverse. And the point at zero temperature separating those multiverses is like a black hole. It's a quantum critical point. And we don't understand those either. Okay? But once we get out to a micrometer, we're already at the scale of life. Okay, and lest you wonder, here's a picture of Mycoplasma mycodes. It's a little bug that lives in your stomach, and it is a fully operational life form. Okay, and it also has the size of a Cooper pair. And whilst we understand the physics of a Cooper pair fairly well in tin and lead, we don't begin to understand the full scale of emergence of Mycoplasma mycodes, okay? And so this is emergence, and it's very palpable, and it leads us to ask, what are the principles that govern emergence of collective behavior in matter between the angstrom and the micron, okay? And we don't understand them fully. How much time do I have? 3 minutes, okay. Well, I'm not going to finish my talk, but that's fine, because I'm really the warm-up band. Here's a little picture about emergence, and let me remind you that emergence began in condensed matter physics with Einstein's phonons. This is the emergent quanta of the solid-state physics. Landau theory is another example of emergence in condensed matter physics. There's also a reductionist path that was amazingly successful. The Wigner crystal, ferromagnetism, Chandrasekhar, the combination of gravity and stat mech led to Chandrasekhar's limit, which is the limit for stability of a star. It's an amazing formula because it involves two scales, the mass of the proton and the Planck mass. Okay? It's the first formula that combines quantum gravity and quantum mechanics, but we haven't got much further since those days, unfortunately. Landau-Ginzburg theory, BCS theory was a convergence of emergence and reductionism, really. Okay. The Anderson-Higgs effect was a direct emergent spin-off from BCS theory, and it led to the idea that we live in a cosmic superfluid in which the Meissner effect is what? It's the exclusion of the W and Z fields from our world, okay? They're coherent, their penetration depth is 10 to the minus 17 meters. Their coherence length is about 10 to the minus 18 meters, and we don't know what happens inside the coherence length of the weak force. Here are some others, and criticality, the idea of scaling, and then, well, I was going to finish off talking very briefly about topology, if I might. Topology is a kind of combination of mathematical emergence and experimental convergence. And it's had many consequences: the discovery of liquid crystals, vortex lattices, the integer quantum Hall effect, the fractional quantum Hall effect, the idea of Z2 topological insulators. Okay? And today, in the 21st century, perhaps we're ready for a new storm of discovery, something that brings together these various threads. I was going to give two examples of emergence in current condensed matter physics. Let me just very briefly touch on them, okay? The rise of topology, this is just a little bit of pictures. Topology in mathematics is a kind of emergent area, and you may have heard of the Langlands program that links topology to number theory, to quadratic and complex forms. But in condensed matter physics, topology turns out to be important for the wave function. And so in mathematics, it links differential geometry to topology. But in physics, we've discovered over the last 30, 40 years that there's a link between the differential geometry of the wave function and quantum matter. And in phase one, there was this marvelous insight that came from experiment on the quantum Hall effect, and the discovery that there's this emergent field in momentum space that describes the entanglement of the wave functions, the Berry connection, which Thouless was able to link to the integer quantization of the Hall constant. And in fact, Haldane took this in a reductionist mode and came up with a little model of which exposed this emergent topology. And his model was on a honeycomb lattice, okay? And a few years later, the discovery of graphene led Kane and Mealy back to his paper, and they said, well, maybe it's topological. And this led to the idea of topological insulators, the idea that when you cross bands at high symmetry points, you introduce a topological texture into your ground state. And this has led to a huge revolution, and the discovery of many new ground states to topological insulators, and it's a very active area of science. And so you can see how emergence and experiment came together to give us a new area of physics, and emergence, experiment, and reductionism. By contrast, okay, I'm going to wrap up then. All right. So let me end by just mentioning, I'll just get to my conclusions. Strange metals are an example of an area which really hasn't been understood, and I'm going to skip past it. Just get to my conclusions. Okay, so I'm just going to leave them there for you to read, but just to mention one last thing. It's a personal belief. I think that just as in classical mechanics, it took 200 years for the field to settle, it'll probably take that same amount of time for quantum physics. So we're right in the middle of it. And although we're 90 years after Heisenberg, Dirac, Born, Bohr, and those other great physicists, maybe, like classical mechanics, there's something emergent that's missing. And that when we understand it, we'll have a whole new perspective, just as energy was to classical mechanics. Thank you.